Hello and welcome to classifying LiDAR ground points using LiDAR360. I'll briefly outline this process, look at some statistics, and determine some ideal parameters. To begin, let's load our LiDAR point cloud. Here, my data has been cut into tiles and uses the LiDAR format LAS. This is typical of many LiDAR datasets. When you first load this data into LiDAR360, it takes some time to generate the indexed version of the data, which this software calls LiDAR. This indexed version is useful for speeding up visualizations and processing. The best part is that it only needs to be done once. Afterwards, the data is forever indexed and will load nearly instantly into your software. For comparison of loading times, I will load the LiDAR version of the dataset. Also notice the size difference of LiDAR and its LAS counterpart. The LiDAR format size is comparable to that of LAZ, the zipped version of LAS. These were both loaded in real time. To begin getting a feel for this dataset, I'm going to start visualizing and interacting with it. There are also shortcuts to view the top, sides, front, and back. Each tile has a boundary that can be viewed by highlighting it in the project window. I want to pick one that represents the entire dataset reasonably well, probably one in the middle somewhere. Using grid statistics, I can start looking at some qualitative information to help me make decisions later. I'll start off using a spacing of 1 meter and viewing the point densities min, max, and mean. Just to have a better idea of what resolution I can generate products at, I'll try different spacings. Now on to classifying the ground points. Here there are a few parameters that should be set to optimize the results. Since I have no buildings in my scan, I can ignore the first one somewhat. The angle parameters can be estimated by taking measurements from the viewer. I'll first measure along the sides using the angle tool. Then do the same on the different faces. It's probably most useful to use the profile viewer to take some measurements within the dataset, so I'll use that and the same angle tool to make some last measurements. And I'll repeat at different cross sections. Just from looking at the elevation changes, I can scope out where the most drastic angle probably takes place. Heading back to the Classify Ground Points dialog, I'll fill in some parameters by setting the building parameter to something relatively small, since there are no buildings, and the angles to something with a little extra buffer from the angles I measured. The iteration parameter should be something we're comfortable with after analyzing the grid statistics. Then click OK to run the classification. This process should take some time to finish. For me, it was about 5 minutes on a laptop. After taking a quick look over of the result, I want to analyze it a little further by viewing just the ground points. Using the Extract by Attribute tool, I'll create a new folder where to export the extracted points. Then specify which class to export by using just to ground. To keep things tidy, I'll first remove the original tiles, then add the new ones. And doing another visual inspection, the result looks pretty good. But let's do another qualitative analysis using grid statistics. Before doing that, I want to merge the tiles instead of using just one to represent the dataset. To clean house, I'll just keep the merged dataset. Again, I'll try different spacings to determine ideal resolutions. I find the mean and the empty value to be the most important when creating rasterized products. We should shoot for a mean of over 1, with higher values being better. The empty value indicates how many spaces will be empty, and this is a good indicator as to the number of grid cells that will not contain a LiDAR point when creating rasterized products. I can create some gridded products using just the ground points, but I'll use the original dataset just after I classified them. Let's create an elevation model using the ground points. 0.5 meter resolution seemed okay given the mean and empty values. I'll also merge the final result to one file. Just viewing the DEM doesn't tell us much. Instead, I want to take a good look at the hill shading by zooming in and looking for any unwanted artifacts. Additionally, we can view a 3D version of the DEM by converting it to a live model. As an example of the artifacts I mentioned, I'll create a DEM at 0.25 meter resolution. Let me take another look at the values I was getting from grid statistics. My empty value indicates that nearly half of the grid cells will be empty. Moving ahead to create the 0.25 meter DEM, I'll again look at the hill shading. Here I notice several places with these strange artifacts, probably a result of patching large gaps. That's all for this one. If you found this useful, please leave feedback. Post any suggestions or questions in the comments below. Thanks, and bye-bye.